Okay, so let's get started. Hello and welcome everyone to our today's webinars, Keras model learns to play piano. My name is Kathrin and I'm one of the data scientists here at Knime. A bit of housekeeping before we start. So we do have a Q&A session in the end of the session. So please ask your questions or type your questions into the Q&A, and I'm looking forward to your questions and to answer them in the end. For your information, the session is recorded and will be available on YouTube, and you will get also the opportunity to download the slides from the Knime forum. Also, as always, all the example workflows which I'm going to show during today's webinar are available on the Knime Hub, so you can really try it out. So what do we want to do in today's webinar? What we want to do is we want to find out whether we can use an AI to generate music. Or more specifically, we want to find out whether we can use piano music from Schumann to train a neural network to generate some piano music. And I actually leave this question now up to you, and I will show you the result right away. And you can decide for yourself whether this actually sounds like piano music or not. And this was now a short play of the music that was generated by the AI that I trained before this webinar. So what are you going to learn in today's webinar? You will learn on one hand how you can train a neural network to generate music, but on the other hand, you will also learn what are the different steps involved in solving a deep learning use case. And we will go really through all the steps, starting from preprocessing, defining a neural network structure and thinking about what kind of neural network structure fits our problem and why, then training the network, and then also applying it. And the first step is always the preprocessing, because no matter whether it's piano music or some other data, neural networks only understand numbers. And therefore, always the first question you need to ask yourself is, what is a good numerical representation for your data? Or in my case, what is a good numerical representation for piano music? And one way of how piano music can be described is actually in a music sheet, like the music sheet or the part of the music sheet you see here in my slides. I now want to focus first only on a small part of it, this part. And as you can see, music in the end is a sequence of notes where we can have different notes, and different notes here are depicted by having these black dots on different lines. And these different notes have also names, or letters can be used to kind of encode them. Therefore, we can encode music as a sequence of notes or a sequence of different classes. But as I mentioned, neural networks or deep learning networks, they only understand numbers. So we also need to encode these different classes then, and therefore we have different options, and two of them are integer encoding or one-hot encoding. What is integer encoding? The idea of integer encoding is to encode distinct classes, in our case distinct nodes, with distinct integer values. So for example, if we would have the classes black, blue, brown, and red, we could encode them with 1, 2, 3, and 4. Or in our case, we have the different nodes, and the different nodes can be kind of considered or can be described with different letters. So we could encode them C with 1, D with 2, E with 3, F with 4, and so on. And this integer encoding is always helpful if we have a natural ordered relationship. Because if we don't have an ordered relationship in our feature, then we actually introduce something into our neural network that is not present, because which is a distance between the different values that we have. And in this case, for example, if black is encoded with 1 and blue encoded with 2, then the distance between black and blue would be 1. But on the other hand, the distance between black and red, which is encoded as 1 and 4, would be 3. So we would kind of tell our network that black and blue are closer to each other than black and red. And with nodes, we could think about an order of having nodes which are lower or higher, but I didn't really want to do so. And that's why I thought about another encoding option. And this is the encoding option of one-hot encoding. What is the idea behind one-hot encoding? The idea behind one-hot encoding is to use a collection of dummy variables. to encode the different values that we have. So if again, we have the different categories, blue, red, green, and brown. 4 categories, we would create 4 different columns, blue, red, green, and brown. And if a feature is present or a class is present, then we get a 1, and otherwise we get zeros. This means we would create as many binary variables as we have different features. And that's what I decided to use as encoding for my different nodes, so that C, D, E, and F get encoded as different vectors where I always have a 1 if this is the next node in the song, or a 0 if this is not the next node. And with this one-hot encoding, I could now encode the sequence like this one, where if I have a G, I say I have the vector 1, 0, 0, 0. And on the other hand, if I have an F, I have the vector 0, 1, 0, 0, 0. And with a sequence of these vectors, I could now encode a sequence of different notes, which would make a piano piece. But actually, this is not all, because as you can see, we have different type of nodes. For example, this one with a dot is longer than these nodes. This means just having a sequence of nodes is not enough to actually have a numerical representation for music. And therefore, as my nodes can have different durations, I need a second sequence which encodes the different durations. And for example, this node tells me, or the type of this node tells me that it's played for 3/8 of a measure, and these others are shorter, they are just played for 1/8 of a measure. And also in this case, I now need to think about how do I want to encode these durations. And also here I have different options. I can either encode the duration as numerical value, then every possible numerical value could be a duration. Or in music, quite often you have different types of durations, like we have 3/8, 1/8, a half, a full measure. So we could also think about, okay, we could encode these different durations again as different classes. But I, in this case, decided, okay, I want to encode my durations as different numerical values. If we look at the full piece of music sheet that I showed in the beginning, we see one more problem. Because at the moment, we would just encode one note after the other. But if we look at this music sheet, we see that sometimes there are also multiple notes played at the same time. We then call it a chord. For example, here in the beginning, I see all these 4 notes should be placed at the same time. And also another issue that we have in music is sometimes another note starts while the other one is still playing. And this is something that we have here as well, because this note is actually played until here, and then this note starts already in between. And we also need to encode this somehow in our numerical representation for music. And therefore, I need a third sequence. And here I decided to use a feature that I call relative offset. What is this relative offset? Therefore, we first need to understand what is the offset. And the offset is the time between the beginning of a music piece until the start of the associated note. But we will use in a second neural network architecture, which takes already kind of care of the sequential order. That's why I thought, okay, the offset itself, which describes the time between the beginning of a music piece and until the note starts, is not really a good feature. That's why I decided I go for the relative offset, which is the time between the current and the previous note. This means if I play 4 notes at the same time, then the relative offset between these 4 notes would be 0. Summarizing, I can say one way of describing music or piano music in a numerical representation consists of 3 sequences. We have a sequence of classes, which encodes the different notes in which order they are played after each other. Then we have 2 numerical sequences, one that encodes the duration of each note, and the other one, the relative offset. As I mentioned, for my neural network, I wanted to use music from Robert Schumann as the training data. And therefore, I was looking for some music where I could get some data that I could use for training. And then I found some MIDI files with music from Robert Schumann on GitHub, which I wanted to use. And the next problem I had to solve was then, how do I extract from these MIDI files this information, this numerical representation of the music, which I can use to train my network. And therefore, I found a Python library, which is called Music21, which allows you to extract different information from MIDI files. And I was using this Music21 library to actually extract the information which I just described. But I actually wanted to use Knime Analytics platform to solve this problem. And therefore, I thought, okay, why don't I mix and match then these two tools? And I use Knime Analytics platform in combination with Python to extract this information from the MIDI files. And here you can see the small workflow which I used for this task. We have here first the list files folders node, where I list the path to all the MIDI files which I downloaded. And then I have here a loop structure where in each iteration I extract the 3 features from the MIDI files using the Python library Music21 in this Python source code node. And here you can see the configuration window of the Python source node. And as you can see, it was just a few lines of code which I needed to actually extract from each of the MIDI files the 3 different features. So what I do here is I first load the different libraries that I use, then I parse the MIDI files, I extract the instruments, and then in this part, I go through the parsed MIDI file and I extract the notes, the duration, and the offset. And the result was then a table, a Knime table again, that looked like this. But if you look at this table, then you probably realize that, okay, we have here the notes, but the notes are not one hot encoded yet, what I wanted to use. And you can also see that if it was a chord, this means that 2 notes were played at the same time, in this case, B4 and B5, then they are not in 2 separate rows, but they are still in 1 row and in 1 cell. In addition, you can also see the duration is not correct yet, because you see the duration is still of type string, and we wanted to have this as a numerical value. And also the offset is still a string, and it's the absolute offset, and I actually wanted to use the relative offset. So I needed to perform a bit more pre-processing on the data, and that's something that I've did then in Knime. So what I did here is, in this meta node, I convert the chords, so if I have more than 1 node, into multiple rows with an offset with the same offset, so a relative offset of 0. And then I process one song after the other, and I always calculate then the relative offset, and I convert the duration into a number. And here I also create a dictionary of all the possible notes that I have in all of the songs, and I apply the dictionary to also encode the different classes. I mentioned I wanted to use a one-hot encoding, but actually I used a 2-step one-hot encoding. What do I mean by this? What you can do in Knime Analytics platform, if you want to use a one-hot encoding when training your neural network, is that in the pre-processing, you can create just an index encoding and then convert this into an index encoding into a one-hot encoding when training the network. This means what I did during my pre-processing is I created a dictionary with a list of all the different notes that I have in my different music pieces. Then I assigned to each node an integer, and I first performed an integer encoding using the cell replacement. And afterwards, I had a sequence of integer values. I created a collection cell out of it. And then in the Keras network learner node, I can use the conversion from collection of number integer to one-hot tensor, so that actually the Keras network learner node takes this collection of integer values into account and creates this one-hot tensor for me when training the network. And the result of this pre-processing looks then like this, that I have my nodes encoded as different integer values, which can be then taken into account by the Keras network learner node later. We have the relative offset as a number, and we have also the duration of it as a number. This means here I have now a numerical representation of my different piano music pieces by Schumann. And then the next step now is to think about which network structure or architecture can we actually use to train a neural network to generate piano music. And as I mentioned already, there is a type of neural networks which is especially useful when it comes to sequential data, like here we have now a sequence of nodes with the relative offset and the duration, which are called recurrent neural networks. And I don't want to go deep into recurrent neural networks in this webinar today, because we had already a webinar about recurrent neural networks in the past. But I just want to give you a brief introduction, kind of as a reminder of what recurrent neural networks are. And as I mentioned, recurrent neural networks, or RNNs for short, are a family of neural networks which are especially suitable for processing sequential data, like in our case, music. And the key idea of recurrent neural networks compared to other neural networks like feed-forward neural networks or convolutional neural networks is a loop connection. And we will see on the next slide what I mean by a loop connection. And recurrent neural networks are used for all sorts of tasks where you have sequential data. For example, if text is also a type of sequential data because text is a sequence of words or characters, and therefore it's often used for text generation or for text classification, but also for time series data, like for example, for demand prediction or stock price prediction. And on my next slide, you now see how a recurrent neural network actually can be depicted. And there are two ways how you can depict a recurrent neural network. We have here on the left-hand side, the so-called rolled representation, where you can also see this loop connection. And here on the right-hand side, on the other hand, you see the unrolled representation. And the idea of a recurrent neural network is that you have a feed-forward neural network that you apply at each time step or as each step in the sequence. This means here, these x1 to x2, x3 could be different nodes. And into this network copy, you always feed the next input in the sequence, but in addition, also a hidden state. And this hidden state is then also created as output at every step. And therefore, these recurrent neural networks have something that is called a built-in memory. Because if I then make a prediction after seeing, for example, 4 nodes, then I make this prediction not only based on the last node, but here through this hidden state, I actually have kind of a memory of all the nodes that I saw before. This means the key idea is kind of here this additional hidden state, which in the first step is kind of an initial hidden state, which could be just zeros. Then we feed into the network the initial hidden state with the zeros, the first input. And then based on this, the hidden state is updated. So we have here the memory that remembers the first or part of the first node as well. And we could also potentially create an output. And these recurrent neural networks have some advantages which are important when it comes to sequential data. One it is that it takes the context information into account because of this memory that we have in this context state. But another advantage is also that it takes the order into account, which is also important because we don't just want to tell the network these 5 nodes were played before, but also it's important in which order these nodes were played. And another nice advantage of recurrent neural networks is that they can handle different sequence lengths. What is also important for us, because in the beginning we might have only 1 node, and then later on we have 3 or 4 or 5 or 6 or 20 nodes, and then we always want to take all of them into account when we predict the next node in our sequence. When we have recurrent neural networks, they can be used in different formats. For example, you can say whenever I have an input in the sequence, that I want to create right away also an output. But sometimes you have also a sequence as input, and just in the end, you want to create an output. And these different architectures of recurrent neural networks are called many-to-many, many-to-one, and one-to-one. If we have a many-to-many recurrent neural network, then we have a sequence as input and a sequence as output. We have this here in both examples. And then there are still 2 ways how you can use a many-to-many network where you have a sequence as input and as output, because you could use it in a way that whenever you have an input, you create right away an output, like here on the left-hand side, or you could also use it in a way that you have 2 recurrent layers and use the first one to first process the whole sequence. And then you have here a summary of everything that was kind of in the input sequence, and then you start generating an output sequence. And a use case for the example network architecture here on the left-hand side would be language modeling, where when you see a start token, you want to predict the first word, then you want to use the first predicted word and predict the next one, and so on. And an example where you would first process a sequence and then start creating the output sequence would be neural machine translation, where we have the sentence in English, then we have here kind of the context all summarized, which we can feed into another recurrent layer, which then starts creating the translated sentence. As I mentioned, sometimes we have also many-to-one or one-to-many during training. And many-to-one means we have an input sequence, but our output is not a sequence, but just one value. And this is, for example, used in language classification or text classification in general, where a recurrent neural network is used to first process the whole sequence, the whole sentence, and then we want to predict, is it English or is it German? And there is also the other way around, that you can have also only one input, but you want to have a sequence as output. This would be one-to-many, one input, many outputs. An example, therefore, is image captioning, where we have an image as input, and then we would create an output sequence as a result. And the question now is, okay, we know we have sequential data, we know we want to use a recurrent neural network, but which architecture can we actually use for music generation? And like often today in my presentation, also here we have different options. You can either go for a many-to-one option or a many-to-many, and I will show you both. So we could train our music generator model in the many-to-one way, where we say, okay, we always give the model, for example, 20 notes, the last 20 notes, to initialize these hidden states, to kind of have a summary of the beginning of a music piece, for example. And based on this, we predict the next note. To train something like this, we would have then always input sequences and then just one target value. And our training data could look like this, that in the beginning, we say we take the first note until the 20th note as training, as input sequence, and the 21st note is our target. And the next training example would be we take the second until the 21st note, and our target would be the 22nd note. If we train a network in this way, then during deployment, we actually also need a start sequence. So we cannot just say, tell the network, start playing piano, but we would need to give it a start sequence, which it can be used, it can use to kind of initialize these hidden states with the first, after the first 20. In this case, we would give the network our start sequence, then it could predict the next word, the next tone in the first iteration. And then in the second iteration, we would start here again with just some initialized hidden states, just zeros, for example, and we would leave out the first tone from the first iteration, but end to the end of the input sequence the last predicted tone. And in this way, we could then over and over apply the model to generate some music. The other option is to train in the many-to-many way. In this case, we don't need a start sequence or a start sequence in the beginning when we deploy our model, but it is trained in a way that whenever we see a character or whenever we see a tone, we also want to output a prediction right away. So it would be like this. If my training data starts with G, my input sequence starts with the tone G, then we tell the network, then predict F. If you see G, F, then predict D, and we would train all of this in once. And for this, the training data has to look then like this, that you have always an input sequence and a target sequence, because it's many-to-many. The input is a sequence, the output is a sequence, or the target is a sequence. And the different sequences are just shifted by one character. This means here we start with the start token, and then we want to predict the first note. And then in the next one, we would start with the first note, but we actually want to predict, and here's a little error in my slide, that should be N2 here and not N3 with the second. If we train our network like this, how can we use this network then during deployment? Then in the first iteration, we also would start with some initialized state vectors at time 0. We would say, okay, G is our first node, start with this G, a song, and then it would predict the first or the second note in the song. And we need also as output the state vectors which were updated. And then in the next iteration, we would need the state vectors from the first iteration. We input them again into our recurrent unit together with the last predicted node, in this case F, and then we would predict the next node, and so on. And we also need here again the state vectors done in the third iteration, and so on. And because I didn't want to provide a start sequence during the deployment, I decided that I want to go for the second option, where I wanted to train a many-to-many. And to create a many-to-many network, I now need to create this input and target sequences. And that's something I've done again with Knime Analytics platform. So remember, we have here our pre-processed music pieces encoded in the way we defined in the beginning. And based on them, we now need to create these input and target sequences. And the most important node for this is actually this leg column node that you can see here. What does the leg column node do? It appends past values as new columns. This means it takes past rows above, and adds the values as additional columns. So for example, if we have here a sequence with x1 until x6, and we define a leg of 3, then it will take the 3 values above a value and add them to additional columns like we can see here on the right-hand side. And with this, we can now create overlapping sequences. The only thing that we need to take care now is that this first value is actually right on the right-hand side, and we need to have it right on the left-hand side. So we use in this meta node, this resort columns meta node, we resort all the columns, and then we can create, based on these sequences, our input and target sequence, which happens in this meta node here, where we remove the first or the last node so that we have these overlapping sequences. And if we look now here at the resulting table after creating this input and target sequences, we see we have here these collection cells, which I created with the create collection column node. And in our input, we always start with 0, which is our start token, and everything is shifted by 1 character compared if we compare the target nodes to the input nodes. Using just a recurrent layer wouldn't be enough for our network, because what we would get out of this LSTM network here is just a really long or a really big hidden state. But what we actually want is we want to get our next node. So a network structure where we would have just an input and then the LSTM, which is a type of recurrent layer, and then right away the output wouldn't work, but we need one additional layer, which we can use to actually predict the next node, the next class. And therefore, we can use the output of the LSTM layer node in a softmax layer, because the softmax layer can give us a probability distribution over all different classes, in our case, over all different nodes. That's why I added in my network structure, in addition to the recurrent layer, also a softmax layer. And then another thing we need to think about is which loss function can we actually use to train this network. And a commonly used loss function, if we have a multi-class classification problem, like in our case, the different classes are the different next nodes, is categorical cross entropy. So we can use here categorical cross entropy to actually train our network. And just to add a little bit more complexity to the network, for the network to be able to really learn the structure of music, I decided to use one additional hidden layer where I used a dense layer with the activation function ReLU, which is commonly used in deep neural networks. And next, I want to show you how you can actually now define a neural network structure like this one in Knime Analytics platform. So let me switch to Knime Analytics platform. I started this workflow already. I read here the pre-processed data. So if I go here at the output port, we see here the input sequence for the node and also the target sequence for the nodes. And already for the second part of the network, the duration and relative offsets. And then we have here, I created just vectors with zeros, which I want to use as the initial state vectors. Then I can define here in the upper part my network structure. And the first important layer that we have in each neural network is an input layer. So I can look for the Keras input layer node. And then in the configuration window, define the shape of this layer. What is the correct shape for our problem? We have sequences with different sequence length. That's why, or potentially different sequence length. That's why I use here a questionnaire, because the first value is always the size of the sequence. And the second value that we need to define is how many values does each input have, And in our case, this is a vector of 79 dimensions because we have 79 different nodes in the different music pieces. Then I will use here a name prefix so I can recognize this later on easily. And I call this nodes. Next, after our input layer for the different nodes, we have an LSTM layer. So I can look for the LSTM layer. See, Keras LSTM, which is the recurrent layer in our network. And into this one, I feed on one hand the inputs into the first part. And optionally, I can also provide here input vectors for the initial states. And to make it easier during deployment, I decided to feed them here into this network as well. Then I can open the configuration window. Here I now need to select which of these inputs is actually my input tensor and which are the hidden states. Then I need to define how many units we want to use. And I want to use 256 units because also my hidden state tensors have 256 units. And because we train a sequence-to-sequence model, it's also important to check this checkbox return sequences because we do need sequences. And we want to use the states always as input during deployment. Later on, that's why it's also important to check here this checkbox return the states. Otherwise, they are not returned, but we actually need them later during deployment. And then we wanted to have a ReLU layer, which is a dense layer, or a dense layer with activation function ReLU. So I can go here to the configuration window and decide again how many units this layer should have and which activation function I want to use ReLU. And then we have our output layer where I use another dense layer. And remember, we have 79 different classes. So we want to have a dense layer with 79 different units. And we want to get the probability distribution over all different classes, all different nodes. That's why I use here softmax. And then I can feed now this network structure into the Keras network learner node. And in this Keras network learner node, I can then define all the learning settings. For example, in which column do I have my inputs for the nodes? And that's why I use the prefix, because here you can also see now, here I define the settings for the nodes. Here I define the settings for state 1. And here, important for the nodes is now I use this conversion from collection of number integer to one hot tensor so that I really have one hot tensor during training. And then in the target data, you can select in which column do you have the target sequences. And most important, also, you can define here which loss function you want to use, which, as I mentioned already, for multi-class classification problems like the one that we have at hand, and categorical cross entropy is a good one. And then in the options, you can define the training settings, for example, how many epochs you want to train and so on. And then you could start training now. And I usually trained my networks overnight when working on this project because it was quite time expensive to train the networks. That's why I won't do it now. If we now would train this network and apply this network, we would have a network which can only predict a sequence of nodes. But remember earlier today, I told you a sequence of nodes is actually not enough. We need a sequence of nodes encoded as classes, but also we need sequences which give us the duration of each node and the relative offset, which tells us the difference between the previous and this node. Therefore, we need to extend this network structure. And therefore, I will go back to my slides. And I have here in the slides also what I've just built with you together. So I will skip this part. So we now need to extend this network where we have as loss function categorical cross entropy to just teach our network to always predict the next node. So how can we extend this network now in a way that it can also predict the duration and the relative offset? And therefore, if we want to have a network that can also predict the duration, then we probably want to feed into our LSTM net layer, not only the nodes, but also the sequence of durations. And then use the output of the LSTM network in another layer to predict also the duration of the next node. And an activation function that we can use here is then again ReLU, because ReLU has only values between 0 and infinity. And that makes also sense for the duration, because the duration is a numerical value which cannot be negative. But then we also need to optimize this value, that we have then the target duration and the predicted duration. Therefore, we need to add a part to our loss function. And here we could add the mean squared error, for example, between the predicted and the true duration of the next node. And we can do the same also for the relative offset, that we feed the sequence of relative offsets already into the LSTM layer. We use the output of the LSTM layer in an additional dense layer with activation function ReLU. And then also here we need to add to our loss function the difference between the predicted and the real relative offset, so that this one is minimized as well. This means now we have into our an LSTM layer which has not only one input, but 3 input sequences. And we have a loss function which has not only one part, but we have different parts, one for the categorical cross entropy for the nodes, and then twice the mean squared error, which always measures the duration between the predicted and real difference duration, and the predicted relative offset and the real relative offset. And then we have also not only one output, but we actually have at each timestamp 3 outputs. This means now we also need to extend our network structure. And here you can see the network structure that I actually used to train the network. And as you can see here, I have again the initial state inputs, which I feed into the Keras LSTM layer. But in addition, I also have 3 other inputs, one for the nodes, similar to what we just defined together. But in addition, also a Keras input layer for the duration and one for the offset difference. And here, again, I need to provide the shape, and the shape in this case for duration is again questionnaire, but this time comma separated with 1, because the duration is always one single value, and the same for the offset. And then we can combine these different inputs using the Keras concatenate layer, so that now I can feed into the Keras LSTM layer not only the nodes, but the nodes, the duration, and the offset difference. This means here as input, I select here not the nodes anymore, but the concatenated input, and I select the states again. I don't change anything here on the number of units. And again, I make sure that I activated the checkboxes return sequences and return states, which is always important if you train a many-to-many recurrent neural network. And then this output of the Keras LSTM layer node is now not only used once, but it's used 3 times, always to feed a hidden layer, and then have an output layer, one for the nodes, one for the durations, and one for the offset difference. Where for the nodes, I still have softmax as activation function with 79 units. And for the duration and the offset, I always used activation function ReLU with just 1 dimension. And then I collect these different layers together with the Keras collect layer node. And then I can train the network again with the Keras network learner node. And you might wonder now, how do you define this combined loss function with categorical cross entropy and mean squared error? That's something that you can do now in the target data tab, because for each output, you get here the part where you can select in which column do we have the target values, and below you can select the loss function for this part. So you can define for the nodes, we want to use categorical cross entropy. For the duration, we want to use mean squared error. And below also for the offset difference, we want to use mean squared error. And with this additional inputs, you get here also in the Keras network learner node in the input data tab, the option to select for each of the Keras network input layer nodes, in which of our input columns do we actually have the values for this input. And then you can train the network and write the network to apply it in a third workflow. We have the preprocessing workflow, the training workflow, and then a third workflow to actually apply this trained network. And remember this slide where I said, okay, what we do during deployment is we start with some initial state vectors, which are just zeros. Then we feed the first node or a start token into our recurrent neural network or into our network. We predict the first one and we take the state vectors. And then in the next iteration, we use these state vectors, the last predicted node, together with the duration and the relative offset. We predict the next one. Again, these 3 values, we have the updated state vectors, which we then can use in the third iteration together with the last predicted values. And that's now also something that we need to implement in a Knime workflow, so that we have something like this, a start token, our recurrent layer, we make our predictions. It's the with the softmax, we get a probability distribution over all nodes. We sample our node, and then we feed this back into our network. And the workflow that I used for this deployment part is what you can see here. Here, I read my trained model. I then use this Keras set output layers node to define all my outputs. And in this case, I want to get the probability distribution. This is why I have output nodes, the offset, the duration, and in addition, also the 2 hidden states. Then I convert everything into a Keras network model, into a TensorFlow network model, because this is a bit faster during prediction. And then I create here my my star token in the hidden states. And then I make my first prediction here in the TensorFlow network executor node. And here again, I select then the outputs that I want to create. And then I have here at the output, on one hand, the probability distribution over the different nodes, my predicted duration, the predicted offset, and also the hidden states. And then I need to sample my first node. That's what happens here in this meta node. And here I also start creating collection columns, which I use to combine the values from the different iterations from this loop that I start here below. And this looks then like this, that I have my last predicted value, the last predicted duration, the last predicted offset, the hidden states that I need. And here I have collection cells prepared to collect the results from the different iterations. And then I start here a recursive loop. Remember, a recursive loop works in this way that the output or the input of the recursive loop end node will be always fed back into the recursive loop start node. So if I have here my state vectors after an iteration, I can feed them back in here as well as the last predicted values. And this means what we do here is actually just similar to above here, is that we use the last predicted values. We apply our trained network together with the hidden states that we use, and then we sample the next node. And the output looks then like this, that I get here always a collection with a sequence of the different nodes together with the durations and the offsets. And here always the last values, which are used in the next iteration to predict the next node with its duration and the offset difference. And then afterwards, I need to perform some post-processing. I need to apply my dictionary again to encode the different classes again with values that can be understood by the Music21 library in Python. And then I have another Python snippet node, which uses now these sequences to actually convert it again into a MIDI file so that I was able to share some music with you in the bit. And there is also an option to listen to your music in Knime Analytics platform, because we have this list audio files node where you can select a MIDI file. And then with the audio viewer node, you could also listen to the piano music or whatever music you want to generate inside of Knime Analytics platform. Okay, summarizing. What are the steps involved in training or in solving a deep learning use case? First of all, we have the pre-processing. And in the pre-processing, you always need to think, what is a good numerical representation for your data? And here we discussed, okay, we need nodes, duration, and offset or offset difference. But after extracting it, we realized, okay, we still need to perform a bit more pre-processing to really encode the classes, in this case, nodes with different numerical values, what we did in the next step. Then you start thinking about the network architecture. And when you start thinking about the network architecture, you probably will find out also some more requirements how to pre-process your data. And that's what we did as well, because we found out, okay, we need to create these overlapping sequences. And that's what happens here in this last part of my pre-processing. Then we have talked about defining and training a network architecture. And here again, you need to have your problem. You need to take your problem into account, think about what are the inputs, what are the outputs, and what kind of layer or what kind of activation function do I need to produce an output that I want. So for example, if you want to predict a class, you probably want to use softmax. If you want to predict a numerical positive numerical value, you probably want to use redo. And then you can train your network. And then after training your network, you also need to think about how can I now apply my network to make predictions. And in our case, we used a recursive loop to actually create or to generate a sequence of nodes together with the corresponding duration, and a relative offset to have some piano music. The topic today, or in today's webinar, was already pretty advanced. We had recurrent neural networks, we had networks with multiple outputs. These are really a lot of advanced topics. But I hope it kind of gave you an idea what are the different steps you need to perform when solving a deep learning use case. But if you want to learn more, then I can on one hand recommend our Codeless Deep Learning with Knime book, or to join our Introduction to Deep Learning course, where we will also talk about these things like the activation function or when to use which loss function to train your neural network. And we will offer our L4 Deep Learning course the next time in the beginning of July. So it's July 11th of July until 15th of July, where we have every day a 75-minute session where we introduce another type of network architecture, but we really start from scratch. So if you want to get started with deep learning with Knime or in general, then it would be nice to see you there again. And if you just want to try it out, you can also find all these workflows on the Knime Hub, and you will find the slides on the forum. And in the slides, you will also find the link to the workflows on the Hub. If you just want to generate some music, you could also just take workflow 03, generate music. There is a trained model included, and hit the generate button. And then afterwards, use the listen to music workflow to actually listen to your generated music. And with this, we reached the end of today's webinar. Thank you everyone for joining. And now I'm happy to answer any questions that came up during the session. So let me open the Q&A tool. And the first question is from Victor. What are the trade-offs for this task in using integer encoding visual one-hot encoding? As I mentioned, both options are possible in this use case. If you use integer encoding, then you would need to think about in which order do these notes actually occur on a piano, and that is a bit more thinking. That's something I didn't want to do, or I was a bit lazy at this point, and that's why I decided to go for the one-hot encoding. I haven't tried both, so it might work better if you use integer encoding because there is some more information, but that's nothing I've tried out. Then we have another question by Christoph. Thank you, Christoph. If you want to consider the volume loudness, is this also an extension like offset and duration, or will this be handled differently? Absolutely, yes. If you want to add loudness or volume and you get this information, I think I didn't have the opportunity to get this information from the MIDI files, but if you have this information, then you could add it in the same way as I added duration and offset. So these are all questions we've got until, and then we have a question from the chat, where to find the recording. And yes, the recording will be uploaded to YouTube. And so you will find it on YouTube, and as well on the forum, as Shantanu just answered in the chat. Any other questions? Okay, if we don't have any other questions, then thank you everyone again for attending this webinar. And if there are some other questions coming up afterwards, feel free to post them on our Knime forum, and I'm happy to answer them there as well. And then I wish you all a nice evening, and I hope to see you soon, either in one of our webinars or in the deep learning course in a few weeks. Yes, have a nice evening, everyone. Thank you. Bye-bye.